Hello, my name is Sexton. I'm an anaesthetist. One of my clinical interests is education, particularly for the primary, where I teach physiology and pharmacology. Today I want to talk to you about a little bit of pharmacology. One of my passions has been understanding structure-activity relationships, and so I know the structures of the vast majority of drugs that are used in clinical anaesthetics. And often when I'm giving tutorials, I'm a bit amazed to find that people have spent many hours working out, just learning by rote, various structures of drugs which may be of interest. And so I'm very keen to save them the trouble and share my codes where you could learn a lot of structures in a really short period of time. So today I'm very keen to share just two of those with you. So I'm going to talk about opiates, and I'm also going to talk about the volatile anaesthetic agents. So hopefully this information will be very helpful to people out there training, wanting to learn a lot of drugs very quickly, and saving their time for learning other things. So let's get on. Today what I'm doing is just showing some of the codes that I use to help me remember a multitude of drugs. So today I thought I'd just share some of my codes to remember the structure of volatile anaesthetic agents. So some of those agents that we might like to refer to are things like cyclopropane, sevoflurane, methoxyflurane, isoflurane, enflurane, also desflurane, diethyl ether, divinyl ether, fluoxetine, phenanthrene, and trichloroethylene. Give me that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So most of these are historic, and the ones that are most commonly used now, of course, are isoflurane, and desflurane, and sevoflurane. So a lot of these, to remember their structure, it's actually given to you in their name. So for example, cyclopropane. Propane is one of the simple alkanes. So the alkanes are just progressively increased in the number of carbons. So methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane are just progressively increasing the number of carbons, and each of those are getting structures. And of course, without any substitutions, there's just hydrogen ions. So there's 4 hydrogen ions, or 4 connections around each carbon. So cyclopropane, so propane means that there's a 3-carbon chain, and because it's cyclo, it's a ring structure. So cyclopropane is just 3 carbons forming a ring with a H2 on each one. And it's interesting, cyclopropane comes in an orange cylinder, and the pin index system for this is 3,6, and that matches its chemical formula, which is a way to remember it. That's sorted. Trichloroethylene. Now, ethylene is not an alkane but an alkene. So what an alkene, the difference between an alkane and an alkene is there's a double bond between 2 of the carbons. So trichloroethylene, ethylene means there's 2 carbons. So instead of being ethane, it becomes ethene. So it's ethylene. There's a double bond between the 2 carbons, and there's 3 chlorides. So chloride, 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 and hydrogen. Now when this gets, you must never use trichloroethylene with soda lime. What soda lime will do is replace this carbon with an oxygen. Soda lime tends, because it's got lots of oxygen and it's got lots of high temperature, that can oxidise a lot of structures. And so it means adding oxygen, or it means increasing the incidence of double bonds. So in this instance, if you take trichloroethylene and you expose it to soda lime, what will happen is this. You get phosgene gas, and that's very toxic. Now divinyl ether, what an ether is where you've just got a structure, usually a hydrocarbon, with an oxygen and then another hydrocarbon. So this is an ether, not to be mistaken for an ester. So an ester will look like this. So it has the carboxy configuration. So if we go back to just talking about ethers, diethyl ether is simply an ether with an ethyl on one side and an ethyl on the other, and then the hydrogens just filling in. So diethyl ether, a very long-standing volatile anaesthetic agent. It's been used since it was originally described way back in the middle of the 19th century. Now, a vinyl configuration is just where you've got double bonds between sequential carbons. So divinyl ether is actually just almost the identical structure as diethyl ether, except you have a double bond between the carbons. So this then becomes H2, H, H, and H2, so you've got 4 connections for each of the carbons. So this is diethyl ether, abbreviated to ether. This is divinyl ether. Fluoroxene. Fluoroxene was the first halogenated ether. Being halogenated being an ether gives it enormous safety over the hydrocarbons, but these features of this weren't really that well recognised at the time, and so it was discarded far earlier than it should have been. But the structure for fluoroxene is your CO3, CH2O, and then just like divinyl ether, just a double bond between the 2 carbons, the hydrogens. So that's fluoroxene. Then there's halothane. So halothane is a hydrocarbon, it's halogenated. It's the simplest hydrocarbon you can get, just simple ethane. And so it's a CF3, and then here you've got a hydrogen, bromide, and a chloride. So it's the only one with a bromide. And like all these agents, chloride gives them potency, so the more chlorides they have, the lower the MAC, the higher the potency tends to be. Okay, the next two I want to talk about are sevofluoride and methoxyfluoride. Let's do those first. Now what's interesting about these is that they are symmetrical. So they're symmetrical along their long axis. So I'll just explain what I mean by that. Sevofluorane, it's called sevofluorane because it's got 7 fluorides. So sevofluorane is an isopropyl methyl ether. So an isopropyl group is 3 because it's propyl, and it's, instead of the main group attaching to the terminal carbon, it attaches to the middle carbon. So the connection's here. That's the ether component and that. So this is an isopropyl methyl ether. This is the backbone of sevofluoride. And as I said before, it's symmetrical. So whatever you have on this side, you have on this side. So this is CF3. So you've got to have a CF3 here. So there's only room for one more fluoride, so that happens to go there. And then you've got hydrogen, hydrogen, and hydrogen. So you maintain your symmetry. So it's sevofluorane with 3 plus 1, so 7 fluorides, which gives it its name. So that's sevofluorane. Now methoxyfluorane is also symmetrical. Now methoxyfluorane actually tells you its structure from its name. So methoxy is simply a CH3O. And all these agents, except these 4, are all methyl ethyl ethers. Okay? So methoxyfluorane is a methyl ethyl ether. So there's the methyl component, and the ethyl component's there. So what goes here, what goes here? For methoxyfluorane, the very next letter closest to the methoxy in its spelling is an F. And so that tells you that the closest connection then is a fluoride on this carbon. So there's 2 fluorides. 2 fluorides because this is one of the symmetrical ones. So whatever's on the top has to be on the bottom. And then over here, what goes here, the next letter in this is an L. And as we know, the chemical abbreviation for fluoride is not FL, it's just F. So that L then is for chloride. So we have a chloride here, and a hydrogen here. So this is the structure for methoxyfluorane. Methoxy-FL. I now have three structures. And these three left, isoflurane, enflurane and desflurane. And these ones have quite complex structures. But what's really interesting about it, if you want to work out a code, is that for the various carbons, they follow, there's only 5 combinations of what can be on the carbons. So, for example, you can have a CF3, you can have a CF2, you can have a CF1 with a chloride, or you can have just a CF1 with hydrogen ions to make up the difference, or you can have no fluorides at all and a single chloride. So these are the 5 possible combinations. So what I've done is worked out a word that reflects each of these, and because there's 5 possibilities here, then I have these equating to vowels in my code. So A, E, I, O, and U. So as you go A, E, I, U, progressively reduce the fluorides. And when there's 2 single fluorides, the one with the chloride, which gives potency, pushes in and comes in first. So that's the basic code for it. Now, if we look at desflurane, as we said, these 3 are all methyl ethyl ethers. Now, what I've done is I'm putting ethyl to the left because E comes before M in the alphabet. So it's an ethyl, methyl, ether. So this will be our first, then second, then third carbon. So if I take my word for desflurane, when you consider desflurane, its boiling point is about 24 degrees. So its partial pressure at 20 degrees Celsius is in the order of 600 plus millimetres of mercury. So its saturated vapour pressure, i.e. its partial pressure at 20 degrees Celsius, is above all the others. And so my word for desflurane is above, A-B-O-V-E. The consonants don't mean anything, but what I've got is A, O and E from my code describing from left to right what each of those carbons are. So this is the A carbon, A, B, O carbon, this is the E carbon. So the structure for desflurane using the code will be CF3, CF1, and then the difference will be just a hydrogen. So just with this code, just add in hydrogens if you need an extra space, oxygen, and then this is the E carbon, so this is CF2, so CF2 and then a hydrogen. So this is the structure for desflurane, going left to right with the ethyl in front of the methyl alphabetically. This is the A, O and E carbon being above, A, B, O, B, E. So that's the structure for desflurane. Enflurane releases fluoride ions. Now, the fluoride ions are non-toxic because it doesn't get as much metabolised as methoxyfluorane. So enflurane will cause higher fluoride ions. So while it doesn't injure the kidney, if you like, acts as a sieve for those fluoride ions. So if you can remember that enflurane, when enflurane is being used, the kidney acts as a sieve for the fluoride ions that are produced. You then have an I, E and E configuration to work out what its structure is. So again, ethyl, methyl, ether, this becomes the I carbon, this becomes the E carbon, and this becomes the E carbon. I, E and E for sieve, for enflurane. So it becomes, now to be the I carbon, then it's got a fluoride, a chloride, and a hydrogen. 1, 2 and 3. And then a CF2 for the E, the oxygen, and then CF2 and a hydrogen to make up. So that then is the structure for enflurane. Isoflurane had a lot of problems with its history, and initially while it was developed in 1965 as an isomer of enflurane, it wasn't used in clinical practice until about the early 1980s. And when you started to use it then, because it had so much potential problems, it was thought to contaminate. The rats in the original study were fed phenol, and so it was thought that isoflurane was causing the hepatic problems that phenol caused. But that turned out not to be the case. So initially, if you were going to be using isoflurane, and there was some doubt about its usage, then you obviously had to have your head switched on. You had to be very astute if you're going to be using it, because it was a controversial volatile agent initially. Anyway, so the issue of isoflurane is isoflurane started with a lot of controversy, and so you had to be relatively astute while you were using it. It turned out to be quite a good agent, very popular agent. But you probably don't need to be quite so astute now to use it, but the utility of A, U and E tells us its structure. So again, ethyl to methyl, this is the A carbon, this is the U carbon, this is the E carbon. So the structure of isoflurane is CF3, C, Cl with a H, O, and then CF2, H. So that's the structure for isoflurane. I'd now like to teach you a multitude of structures that relate to the narcotics. And so the sort of agents I'd like to teach you the structures of are morphine, hydromorphone, codeine, hydrocodone, dihydromorphine, dihydrocodeine, oxymorphone, oxycodone, heroin, nalorphine, naloxone, naltrexone, and nalmorphine. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So let's teach you 13 drugs very, very quickly. Firstly, these drugs are all based on the basic phenanthrene ring, which is aromatic at the top, and then 3 other rings that have all lost their double bonds except for one position at the bottom. This has an oxygen cross bond, and then at right angles to this position we have 1, 2, 3, a piperidine ring, so a 6-sided ring, 1, 2, 3, 4, 5, 6, 6-sided ring with a nitrogen. So this is a basic ring structure. Now, numbering, it goes 1, 2, 3, which is really important, 4, 5, 6, which is really important, 7, 8, then 9, 10, 11, 12, 13, then 14, which is really important, then 15 on the piperidine ring, 16, and 17, which is very important. So there are 3 critical areas on this four critical areas here. So there's the 3 position, the 6 position, the 14 position, and the 17 position. So they're the ones that are important, they're the ones that change. And there's a very, very simple code that you can apply so that you can, from their names here, you're able to get the structure correct every single time. So we take, the first principle is that on the 3rd carbon, the default is always a hydroxyl group, except if you're in the codeine family. So if you've got codeine in your name here, then it's on C3, instead of having a hydroxyl group, you'll have a methoxy group. So for example, nalorphine is not in codeine's family, so it'll have an OH here. Morphine will have an OH here. Now the next rule is at C6, down the bottom of the molecule. So the bottom of the molecule relates to what's happening at the end of the structure. So if your word or name of the drug ends in INE, morphine, codeine, whatever, then C6 will have an OH on it. If the name ends in ONE, then C6 will have a double bond O on it. And there's a single episode with nalmorphine. If it ends in ENE, and it's just like all the alkenes, so if the name ends in ENE, then it's a C double bond CH2. So you have a double bond CH2 coming off here for nalmorphine. Another point of note is that if there's a double bond at C, if you look at this port area here, if there's a double bond, you can only have a maximum of one double bond here. So if you have a double bond here because you've got hydromorphone, so you've got a double bond O here, you'll lose the double bond between 7 and 8. So you can have a maximum of one double bond in this port at the bottom of the molecule, but you can have none, but you cannot have more than one. So whenever you have a double bond O or a double bond CH2, you lose a double bond between 7 and 8. Now move on to C14, and as you see there, it has a bit of a Y shape. But if you get a OH substitution on C14, as in like that, then you've now got an X shape in the structure. And that it tells you that you've also got an X in the name. So, oxycodone, oxymorphone, naloxone. These all have X's in their name, and what they also have is an OH on 14 that makes this X-shaped. So, if it doesn't have an X in its name, it doesn't have an OH on 14. If it does have an X in its name, then it does have an OH on 14. And the final principle I want to talk about is what's happening at 17. So if it's got a nal in the name, as in nalorphine and naloxone, then what it has is a propylene group attached to N17. And a propylene is just 3 carbons with a double bond between the distal one. So that'll be a CH2, CH1, double bond CH2. So that's true for nalorphine and naloxone. And we'll talk about these other two after. So, looking at those principles, let's now work out what some of these drug structures are. So let's start with our basic structure. So let's start with morphine. So aromatic oxygen across there, double bond there, pyridine ring there. Okay. So morphine does not belong, if you start at C3, morphine does not belong to the codeine family, so there's an OH here as the default. Morphine ends in INE, not ONE, so it's an OH here as the default. Morphine does not have an X in its name, so it does not have an OH at 14. And morphine doesn't have a nal in its name, so it just goes to the nitrogen here for the default here, which I may not have said before was just a simple methyl group. So that's the default for the basic structure. So that is the structure of morphine. Now if we were to turn morphine into codeine, put a line through that. If we were to turn morphine into codeine, all we have to do is to go to C3 and put a methoxy here, CH3O. And that has now become codeine. Now if we take codeine, which is what we now have here, and we turn it into hydrocodone, okay, hydrocodone, the hydro doesn't really mean anything. The codone, the ending, tells you that what you've got to have here is a double bond O. So if you're going to have a double bond there, you lose the double bond between 7 and 8. So for hydrocodone, hydrocodone, what you've got, this is a codeine family, so C3 has a methoxy, ends in ONE, so double bond O here. There's no X, so no hydroxyl group at 14. There's no NAL in the name, so this is the structure for hydrocodone. And to turn hydrocodone into hydromorphone, all you do is restore the OH there. Now, dihydromorphine and dihydrocodeine. Let's just restore this to morphine. So OH there, nothing there. So this is morphine with a double bond. Now dihydromorphine says that you've got a morphine molecule and you're adding 2 hydrogen ions to it. So if you add 2 hydrogen ions to this, the only way you can do that is to get rid of that double bond. So if you get rid of this double bond between 7 and 8, but the molecule otherwise stays identical to morphine, then what you've produced is dihydromorphine. And dihydrocodeine, again, is just replacing the OH-3 with a methoxy. So methoxy there, OH there, single bond there. That has got to be dihydrocodeine. Now let's draw oxymorphone. We'll start with that. Now, oxy, so it's an excess, that tells you that you've got an OH here at 14. Oxy. Morph, that tells you it's not in the codeine family, so you've got an OH up here in 3. Oxymorphone ends in ONE, means you've got a double bond down here, and you'll lose this double bond here. Now heroin, what is heroin? If we go back to the morphine molecule, it's good to rewrite these out every so often because it all becomes a bit messy. So now we want the structure for heroin. Heroin's other name is diacetylmorphine. So if we draw the basic configuration, okay, this is morphine. So this is morphine. Now to produce heroin, we want diacetylmorphine, so it's 3,6-diacetylmorphine. So this becomes an acetyl group. And you have another acetyl group down here in 6. And that gives you diacetylmorphine, which is heroin. Okay, let's now do nalorphine. So here's your basic structure. So nalorphine, it's got the NAL configuration. So you have a propylene here. So CH2, H1, H2. That's a propylene group with a double bond between the 2 distal carbons. Nalorphine ends in INE, so it's got an OH here in 6. Nalorphine, it's not in the codeine family, so you've got an OH up here. And there's no X in nalorphine, so there's no hydroxyl at 14. So this is the structure for nalorphine. Now naloxone. Naloxone has an almost identical structure, except for what's happening at C6. So what you'll have at C6 is you'll remove the hydroxyl and you'll get a double bond O. Naloxone ends in ONE. So you have a double bond there and you lose the 7-8 double bond. So naloxone structure, not in the codeine family, OH there, ends in ONE, double bond O there. Now, naloxone does have an X, so it's got an OH at 14, it's got a propylene at 17, so that's the structure for naloxone. Now what's really interesting is naloxone, naltrexone and nalmorphine are all closely related. So if we take, this is naloxone, and to turn naloxone into naltrexone we make one single change to the molecule. And to change naltrexone into nalmorphine, we make one other single change to the molecule. So to produce this is naloxone. To produce naltrexone, all we do is we get rid of this double bond between these two carbons, and we add another carbon, like cyclopropane. So this, forming this configuration, produces naltrexone, just that tiny little change there. That's naltrexone, and to turn naltrexone into nalmorphine, if there's a single change that is needed to do that, the change becomes obvious in the ending, and so to turn naltrexone into nalmorphine, all you do is remove this oxygen here and make this CH2. So you have two carbons together with a double bond between them, makes them an alkane type drug. So that's the structure for nalmorphine. Okay, so that's all we want to talk about today. Thanks very much.